In this lecture, we're going to go over interpreting the Kelvin-Planck statement. Recall that analytically, the Kelvin-Planck statement says that W cycle has to be less than or equal to 0 if we have a single reservoir. Using idealizations, the Kelvin-Planck statement can be used to make several deductions. First, we assume that the thermal reservoir and the portion of the surroundings with which work interactions occur are free of irreversibilities. This allows a less than sign to be associated with irreversibilities within the system, and equal to sign to be employed when there's no internal or external reversibilities. Basically, what we're saying is that W cycle, which is less than or equal to 0, if it's less than 0, it has internal irreversibilities. If it's equal to 0, there are no internal irreversibilities. We're going to look at how that applies to power cycles that interact with two reservoirs. If we consider the system shown in the figure, which is executing a cycle while communicating thermally with two thermal reservoirs, a hot and a cold one, and developing a network out, our thermal efficiency is W cycle over QH, which is 1 minus QC over QH, where QH is the energy received by the system from the hot reservoir, and QC is the amount of energy discharged from the system to the cold reservoir by heat transfer. If QC were 0, the system would withdraw energy QH from the hot reservoir and produce an equal amount of work while undergoing a cycle. The thermal efficiency of such a cycle would be 100%. The amount of operating in such a way would violate the Kelvin-Planck statement and thus is not allowed. Therefore, for any system executing a power cycle by operating between two thermal reservoirs, only a portion of the heat transfer from QH can be obtained as work, and the remainder must be rejected to the cold reservoir as QC. Therefore, the thermal efficiency must always be less than 100%. This conclusion that the thermal efficiency has to be less than 100% applies to all power cycles, whatever their details of their operation may be. So we have some corollaries to the second law for power cycles. Since no power cycle can have a thermal efficiency of 100%, it's of interest to investigate the maximum theoretical efficiency. The maximum theoretical efficiency is evaluated with reference to the following two corollaries. The thermal efficiency of an irreversible power cycle is always less than the thermal efficiency of a reversible power cycle, which operates between the same two thermal reservoirs. And all reversible power cycles operating between the same two thermal reservoirs have the same thermal efficiency. A cycle is considered reversible when there are no irreversibilities within the system, as it undergoes a cycle and heat transfer between the system and the reservoirs occurs reversibly. So if we're going to look at the first corollary, so based on our discussion of the second law, we know that in the presence of irreversibilities during the execution of a cycle is expected to have a penalty. So if we have two systems operating between the same two reservoirs, each receives the same amount of energy Q in from QH. If one system executes a reversible cycle and the other an irreversible cycle, you can conclude that the work developed by the irreversible cycle is going to be less than that of the reversible cycle. Thus, it is going to have a lower thermal efficiency. The second corollary refers to reversible cycles. all processes of a reversible cycle are perfectly executed. So if two reversible cycles are operating between the same thermal reservoirs and each receive the same amount of energy, but one produces more work than the other, it could only have been a result of using some more advantageous selection for the substance used in the process or the series of processes that make up the cycle. The second corollary says that this can't happen and that both cycles will have the same efficiency regardless of your choice of working substance or the series of processes present in the cycle. We can also apply the second law to refrigeration and heat pipe cycles. Just like for power cycles, the second law of thermodynamics places limits on the performance of refrigeration and heat pump cycles. We consider the figure in which the state system undergoes cycles between a hot and cold reservoir, and the direction of the energy transfer is given by the direction of the arrows in the figure. The cycle can either be a refrigeration or heat pump cycle, depending on whether its function is to remove energy from the cold reservoir or to deliver energy to the hot reservoir. For a refrigeration cycle, our coefficient of performance beta is equal to QC over W cycle, which is equal to QC over QH minus QC. If it was operating as a heat pump cycle, we would have our coefficient of performance gamma is equal to QH over W cycle, which is equal to QH over QH minus QC. As the work input tends to 0, our coefficients of performance approach infinity. If work was 0, the system would take energy from the cold reservoir and deliver it to the hot reservoir. This violates our Clausius statement of the second law and is not allowed. There's also some corollaries for the second law for refrigeration and heat pump cycles. They're very similar to the ones for power cycles. They state that the coefficient of performance of an irreversible refrigeration cycle is always less than the coefficient of performance of a reversible refrigeration cycle when each operates between the same thermal reservoirs. All reversible refrigeration cycles operating between the same two thermal reservoirs have the same coefficient of performance. The counterpart corollaries for heat pumps are the same, just replace the words refrigeration cycle with heat pump cycle. Again, let's look at the first corollary to get a better idea of what's going on. We have the figure to the right, which shows both a reversible and irreversible refrigeration cycle operating between the same thermal reservoirs. Each cycle removes the same energy QC from the cold reservoir. The irreversibilities present during the operation of the irreversible cycle are expected to cause penalties. Therefore, if two refrigeration cycles operate between the same thermal reservoirs, you would expect the reversible cycle to require a greater amount of work input to achieve the same output. And since we have to put more work in to get the same output, we will have a lower coefficient of performance. As with power cycles, two reversible refrigeration or heat pump cycles that operate between the same cold and hot reservoirs have the same coefficient of performance. The last thing we need to introduce before we can actually solve any problems is how the Kelvin temperature scale can be related to our definitions of the second law. From our Carnot corollary, we know that all reversible power cycles operating between the same two thermal reservoirs had the same thermal efficiency, regardless of the nature of the substance making up the system executing the cycle. Since the thermal efficiency is independent of these factors, its value can be related only to the nature of the thermal reservoirs themselves. As it's the temperature difference between the two thermal reservoirs that is the driving force behind the heat transfer that occurs, which leads to the production of the work. It can be reasoned that the thermal efficiency depends only on the temperatures of our two reservoirs. That is basically what we're saying is that QC over QH for a reversible cycle is some function of our hot and cold temperatures, where Theta C and theta H denote our temperatures of our hot and cold reservoirs, and psi is some function that we don't know. The expression only applies to systems undergoing reversible cycles while operating between two thermal reservoirs. The above equation gives the basis for defining the thermodynamic temperature scale that is independent of the property of any substance. While alternative choices for the function can't be chosen, the Kelvin scale is obtained by making a very simple choice, which is namely that psi is equal to Tc over Th. This tells us that Qc over Qh for a reversible cycle is equal to Tc over Th. What we're going to do is we're going to use this to define the maximum performance for our cycles operating between two reservoirs. Basically, we're going to put everything together from our Kelvin-Planck statements. We know that the thermal efficiency of an irreversible power cycle is always less than the thermal efficiency of a reversible power cycle when it operates between the same two thermal reservoirs. The coefficient of performance of an irreversible refrigeration cycle is always less than the coefficient of performance of a reversible refrigeration cycle when operating between the same two thermal reservoirs, and that the coefficient of performance of an irreversible heat pump cycle is always less than the coefficient of performance of a reversible heat pump cycle when it operates between the same two thermal reservoirs. It follows that the maximum thermal efficiency and coefficients of performance in these cases are achieved only by reversible cycles. So for a power cycle, our maximum efficiency is 1 minus Tc over Th, where we're using that definition of our temperature scale system from previously. And then we have our refrigeration cycle, where beta max is equal to Tc over Th minus Tc. And then we have our heat pump, where gamma max is equal to Th over Th minus Tc. Please note that Th and Tc have to be in Kelvin or Rankine. The maximum efficiency for a power cycle is also known as your Carnot efficiency, and your Carnot efficiency increases as Th increases and or Tc decreases. So we're going to look at two quick examples of how to evaluate cycles. We have a power cycle operating between two thermal reservoirs receiving energy QH by heat transfer from a hot reservoir at 2000 Kelvin, and rejects energy QC by heat transfer at a cold reservoir at a temperature of 400 Kelvin. For each of the following cases, we want to determine whether the cycle operates reversibly, irreversibly, or impossibly. So the first thing we're going to do is find the max thermal efficiency. Our maximum efficiency is 1 minus Tc over Th, which is equal to 1 minus 400 over 2000, which is equal to 0.8. So the first case, we're given that QH is equal to 1,000 kilojoules and our efficiency is 60%. This one's pretty simple. Since eta is equal to 60%, 60% is less than 80%. So our cycle operates irreversibly. In case B, we are given that QH is 1,000 and W cycle is 850. Our efficiency is W cycle over QH, which is 850 over 1,000, which is 0.85. Our efficiency is greater than our max efficiency, so our cycle is impossible. The last case that we're given is QH is 1,000 and QC is 200. We can do our energy balance to get W cycle. We know that W cycle is equal to QH minus QC, which is 1000 minus 200, which is equal to 800, and our efficiency is 800 over 1000, which is equal to 0.8. Our efficiency is equal to our max efficiency, so our cycle operates reversibly. The next example we're going to do is one for a freezer. By steadily circulating a refrigerant at low temperature through passages in the walls of the freezer compartment, a refrigerator maintains the freezer compartment at -5 degrees Celsius. When the air is surrounding the refrigerator is at 22 degrees Celsius, the rate of heat transfer from the freezer compartment to the refrigerator is 8,000 kilojoules per hour. And the power input required to operate the refrigerator is 3,200 kilojoules per hour. We're asked to determine the coefficient of performance for both a reversible refrigeration cycle and our real cycle, and then determine how the cycle is operating. So our coefficient of performance is our QC over our W cycle, which is our 8,000 kilojoules per hour over our 3,200 kilojoules per hour, which is a coefficient of performance of 2.5. Our max performance, beta max, is equal to TC over TH minus TC, which is 268 Kelvin over 295 minus 268, which is 9.9. Our coefficient of performance is less than our max, so the cycle operates irreversibly. There are many more examples in the lecture notes for you to review and us to go over during class time. In our next lecture, we're going to go over Carnot cycles, which will bring us to the end of chapter 5.